Hi, physical geographers. So we are moving into from topography of arid regions to glacial modification of terrains. We're kind of getting into more niche, specialized areas that essentially these are concepts we talked about earlier in class. Good stuff. Okay, so our outline we typically do impacts of glacier on landscapes. We're going to talk about mountain and continental glaciers, glaciations past and present, so contemporary glaciation going backwards into Pleistocene glaciation, formation and movement, change from snow to ice, erosion by glaciers, transportation and deposition by glaciers, as far as the impacts they've had. Continental ice sheets, so massive glaciers, development and flow, erosion, deposition, and glacial fluvial features. Some of the glacier activity and size, the amount of size and strength and amount of time related to them is very difficult to grasp in terms of a concept. It's just so enormous compared to what we see in our lifetimes. Really fascinating. Mountain glaciers, erosion by mountain glaciers, perglacial environment, pattern ground, proglacial lakes, um, climate factors affecting the Pleistocene Ice Age. And are we still in an ice age? We're talking about such massive amounts of time. And one of the things that is discussed a lot as far as climatology, and that is, oh yeah, we've seen the temperature go up 1 degree in 50 years and it may continue to go up. Well, how statistically significant when we look at glaciers and we're looking at these time periods, we're really talking about hundreds of thousands and millions of years in many cases that we're studying. So anyway, how statistically significant, it tends to be a point of contention, 50 years versus several million, so forth. Okay, so what is a glacier? Moving or flowing mass high up in a mountain valley or a polar plain. Okay, so it can be in the mountains, can be a mountain valley, can be on a big opening plain. So patterns of movement we really see with respect to what I was just explaining. Mountain glaciers in terms of the mountains and mountain valleys, the continental ice sheets in terms of the polar plain. So we have highland ice fields, valley glaciers, relatively straightforward alpine glaciers. High in the mountains, cirque glaciers, very small alpine glaciers defined at basins. See some examples of continental ice sheets where we still see that with Antarctica, with 98% of Antarctica covered by one massive ice sheet. So we talk about Pleistocene epoch began almost 3 million years ago, and due to cooling at high latitude, high elevation areas, we had massive ice accumulation. Ice covered 1/3 of the total land area. Essentially just a massive amount of ice, right? So past and present, we see a comparison of what type of glacial we've had during the Pleistocene period, and then tends to be a huge amount of landmass, about a third. Indirect effects, ice never existed where it's directly unaffected. In the polar glacial zone, so essentially had no impact in some of the world. Sea level changes resulted from the buildup of ice on continents, less water available on continents, lowering the sea level. So essentially the moisture that we have in the seas actually turned into ice. It's a simple way of looking at that. Pluvial effects of past rain periods saw increased moisture due to a combination of meltwater runoff. So we saw different types of moisture activities. And we also had Pleistocene lakes, large freshwater lakes formed in basins of the interior. Here we see some examples to the right of essentially some lakes formed over Utah and Nevada. At contemporary glaciation, what we see today, ice covering about 10% of the Earth's surface compared to a third, and over 96% in Greenland and Antarctica, and I think Antarctica is actually higher than that. Represents about 2/3 of the Earth's freshwater. Antarctic ice sheet, see a sample of that. Ice 2,000 meters thick, so we got some ice that's over a mile thick. Fascinating. Contemporary Greenland ice sheet, see an example of that. As the saying goes, Greenland is ice and Iceland is green. So, perfect example of that. Greenland being right next to the North Pole. Climate change, talk about basically close to 1/4 degree per decade. As I mentioned before, it's about 1 degree for the last 50 years. What's so significant about that? We really did not start getting good weather data really anywhere in the world, even the United States, till 1950s. So, and we do know that the Earth was a lot colder. So kind of, I'm sure there's concern about gases and human impacts as far as global warming or climate change, or there's been different names it's called. But also, I think we need to take into account there's been a lot of things happen to the Earth and what is statistically significant. Okay, ice glacier functions. Accumulation, addition of ice, incorporating snow, ablation, wastage of ice through melting and sublimation. All kinds of terms here. Change from snow to ice. We see with ablation, may be affirmed as more time and compression cause granules to coalesce and grow more dense. Glacial ice results as further compression of air out of pore spaces. So we can kind of see how different ice is formed. Accumulation zone, the ablation zone, the equilibrium line. So we see where upper portion of new ice is formed with snowfall. Ablation with new ice added each year is less than the amount lost, so we're actually losing. There's a net loss with the glacier. Two types of movement. When we get into formation, we're getting into movement. Plastic flow of ice, slow, non-brittle movement ice under pressure. So think of it as moving downward, nothing really stopping it. Basal slip from the bottom, so basically there's a loss of the friction points exceeded, so essentially it can't be held in place anymore. Flow versus advance, as long as the glacier exists, ice is flowing downhill or laterally outward. Even during retrade ablation, ice continues to flow forward. So it's really interesting. Gravity extraordinaire. Okay. Erosion by glaciers, glacier plucking, rock fragments, grabbed as meltwater refreezes. There's also deposits, like if you go into, I know there's some in central Kansas, but that's not the only place, that you can find these rocks that are called erratics. They're essentially been carried a long ways by glaciers that don't have any similarity to the rocks that were formed in the lithosphere of the specific area. They're all of a sudden dropped. That's why they're called erratics. So we see some glacier movement that carries things quite a bit. So this glacial plucking is an example of that. So we see erosion by glaciers, usually long scraping, as this picture indicates. Load is glacial flour, usually finely ground rock. Rock is usually had a lot of compression and rubbing on it, causing some of the grounding. Depositions, we see drift, till, glacial erratics, which is what I was referring to earlier. Glacial fluvial deposition, so water deposition, stream carrying sediment. And ice sheets, so that'd be like Antarctica and Greenland, massive ice sheets. Roche-Montagne, bedrock hidden overridden by glacier. So we see examples of this in California. Yosemite National Parks, good pictures of that. Yeah, deposition of ice sheets, moraines. So we have different types of long ridges or regular landforms, largely made of till. So terminal moraines, recessional moraines, ground moraines. List goes on. Kettles and drumlins. So kettles are regular depressions. So it's kind of like their own little landform tied to glaciers. It's pretty fascinating. So irregular depressions, large block ice, by retreating glacier. Dramas are long, elongated hill of unsorted till that forms parallel to the direction of ice movement. Okay, so you see all kinds of formations, drumlines down here. Definitely seeing the kettles further down. So drumlines, you kind of see the elongated shape. And other features, glacial fluvial stratified drift. So we'll see some drift as far as moving. Eskers, long curvy ridges, glacial fluvial gravel. So we'll see long ridges with gravel. Landforms, we have outwash plains of valley trains, outwash plains of smooth alluvial aprons, deposits or recessional or terminal moraines. Valley trains, deposits of alluvium beyond the outwash plains. So we kind of see these as some bigger parts, and then they have some pieces, for instance, outwash plains and alluvial aprons, some smaller pieces, and gravel that are deposits and formed through the glacier movement. Mountain glaciers, development flow of alpine glaciers, erosion and transportation of rock debris reshapes slopes, steeper and higher relief. So we see the glaciers really causing steep change in elevation. Cirque, as far as hollowed out top of the glacial valley of basin. So that kind of created up high. You can see some of those at the top of Rocky Mountain National Park. The Alpine Visitor Center. Arete, narrow ridge forming, cirques cut into interfluve on opposite sides of the divide. So we see some pretty good examples of that. See an example of the cirque. Picture there. Good. And horns, steep-sided pyramid-shaped mountain peaks. So we see some pretty good examples of horns. Glacial trough, glacial, unlike water, fluvial geomorphology or water flow that basically carves up the earth. You usually see V's. Usually at glaciers, you see U shapes, right? So glacial steps, you can see basically steps that occur down. Paternoster lakes, small lakes formed in depression of the glacial steps. So these fit right in with each other. Okay. Hanging valleys, see a great example of that, Yosemite. Deposition of alpine glaciers, so lateral moraines and medial moraines. Kind of depends on the obstruction or resistance. Proglacial lakes form when ice crosses against the general slope. Pattern of ground, freeze-thaw cycle slowly disrupts uniform soil and regolith, so we kind of see stopping and starting, if you will. Theory of what causes most ice ages must account for four main features: accumulation of ice in both hemispheres, or everywhere, current development of pluvial conditions in dry land areas, multiple cycles of advance and retreat, eventual total or near total deglaciation. So we really need to account for the cycles and the change, is the bottom line. Climate record from oxygen isotope analysis shows a sequence of major glacial and interglacial episodes. So we've had several. Based on the same type of sampling that we use for any type of climate. Even the most recent climate studies, which a lot of it's been ice core samples out of Antarctica. Milankovitch cycles correlate with some, but not all major glacial advances. So we don't really have it fully explained. Other factors, triggered glacial episodes, variation in solar output, levels of carbon dioxide, positions of continents, configuration of ocean circulation, atmospheric circulation, so forth. That we even had meteor hitting the earth, causing a bunch of dust to kill the dinosaurs. We've got all kinds of fun explanations. But none of these alone or together or fully explain the Ice Age or Pleistocene climate. So we've learned a lot, and we have a lot to figure out.